Every atom in your body was forged in a star long before Earth existed and long before your name was ever spoken. The early universe was so hot and so dense that matter could not keep a stable shape. Everything was a restless plasma of light and particles with no quiet boundary. Tonight, we ask what it means to speak of before, if the first page of our history is the moment when time itself begins to flow. Welcome to the Drowsy Astronaut. Here we drift deeper into the cosmos, while gently setting aside the troubles of your day, so you can relax or even fall asleep while your subconscious wanders through the story of time before time. So let's begin. Think of a quiet kitchen late at night. A candle flickers, a ribbon of smoke rises, and a cup of tea cools with steady patience. In that room, time is simple. It is the direction that heat prefers, from warmer to cooler, from order to disorder. The arrow of time is written into that cooling cup. Entropy grows, memory looks backward, and expectation leans forward. In the universe, the same arrow appears. The early cosmos was smooth and ordered, and from that state, complexity had space to grow. Every story has an origin, and cosmology calls ours the Big Bang. But the name can mislead because it was not a fireball expanding into emptiness. It was space itself stretching, distances growing, galaxies drifting apart, not by moving through air, but by the expansion of the fabric that holds them. Picture a balloon, dotted with ink marks. As you inflate it, every mark moves away from every other, not because they travel, but because the surface itself grows. Reverse that motion in your mind. Shrink the balloon, heat rises, density grows, and eventually equations collapse into singularity. The singularity is a warning sign, not a physical marble at the center, but a limit where mathematics breaks. Our equations of general relativity stop giving answers. They predict infinite density, infinite temperature, infinities that are not physical states but signals of failure. At that limit, physics demands something new, a better language, a deeper theory, to describe conditions where space-time itself begins to behave differently. And so we ask what it means to talk of before, whether time itself is emergent, and whether the question belongs inside physics or outside it. Consider, again, your candle and cup. Heat flows outward, entropy grows, the arrow points one way. If entropy always increases, then the past must have been more ordered. The beginning must have been remarkably smooth. Roger Penrose has argued that this smoothness is the real puzzle, because gravity prefers to clump, to form black holes, not to remain evenly spread. In that light, the Big Bang is not simply a hot start. It is a special low-entropy beginning, one that still waits for full explanation. One proposal is inflation, a brief epoch when space expanded at an accelerating rate, ironing away irregularities. Inflation explains why the universe is nearly flat, why it looks the same in all directions, and why small quantum fluctuations became the seeds of structure. Imagine your cloth stretched across a table, tug two corners, the wrinkles flatten, the sheet looks smoother, and small creases become wide patterns. Inflation did this to the cosmos, smoothing space, stretching fluctuations, and setting the blueprint for galaxies. The evidence is written in the cosmic microwave background, light released when the universe cooled enough for atoms to form. That light still bathes the cosmos today, stretched into microwaves by expansion, faint but measurable. Those ripples are like echoes of sound, waves frozen into the light, carrying the fingerprints of conditions billions of years ago. From that pattern, we infer geometry, composition, and history. The cosmos itself tells us the story of its youth. But when we trace backward mathematically, inflation itself must have started somewhere. And the question returns, what set the stage? If inflation requires initial conditions, then the puzzle shifts. What mechanism produced the inflating field? What boundary began the process? Here is where speculation grows. Some imagine an eternal inflation spawning bubble universes, a multiverse of regions, each with its own laws. Others suggest a bounce, where a contracting universe rebounded into expansion, avoiding a singular start. The bounce idea comes from loop quantum cosmology, where space itself is quantized like atoms of geometry. At high densities, that granularity resists compression. Instead of singularity, space rebounds and expansion begins. Think of folding cloth tighter and tighter. At some point it resists, it cannot fold further, and when you release it, springs outward. That analogy captures the bounce, a cosmic rebound from contraction to expansion. Another idea is the no-boundary proposal, introduced by Hartle and Hawking. In this picture, time is not extended backward. Instead, it curves into a rounded geometry like the North Pole of the Earth. Beyond the pole, the question of further north is meaningless. The map itself ends not with a wall, but with smooth curvature. Likewise, before the Big Bang may be meaningless. Time itself may have curved into space, with no earlier tick to count. Cyclic models offer another possibility. Universes that repeat across eons, each expansion following a collapse. Penrose's conformal, cyclic cosmology suggests that a far future, thinned of matter, stretched of scale, becomes mathematically identical to a new beginning. Imagine an old symphony fading to silence, and the silence itself reshaped as the opening note of a new performance. That vision makes our universe one act in a play of many, each act following from the last across unimaginable times. But all these ideas must face the same demand: observation. Science cannot rest on elegance alone. Theories must predict signals, imprints we can look for. Non-Gaussianity is one such signal, a statistical fingerprint in the ripples of the cosmic background. Gravitational waves are another, faint curls of polarization in the microwave sky, a whisper from the earliest instants. So, far the sky is quiet, nearly scale invariant, nearly Gaussian, nearly flat. The data favor simplicity, not wild irregularities, but calm consistency. Still, the search continues. Instruments grow sharper, surveys wider, patience deeper. Each measurement rules out families of models, pruning speculation, guiding us closer to truth. Think again of your hand near the flame, the warmth fading, the arrow leaning forward. Entropy is the law that makes time directional. It is why we remember the past, not the future. The early cosmos was improbably smooth, its entropy low, its potential for growth immense. That fact is as important as expansion itself, for it defines why time has a direction at all. Language strains here, because our words evolved for kitchens and streets, not for quantum gravity. We say before and after, but at the edge of time, those terms may not apply. Perhaps time is emergent, built from correlations, from relationships between changing systems. In that spirit, the no-boundary condition is a law of origin, not a prior tick, but a state from which time emerges. In the bounce, there truly is a before, a contracting cosmos leading into expansion. Both are possibilities, both consistent with certain interpretations of theory, both waiting for evidence. The sky itself must decide, through signals buried in its oldest light. Think of a domino line resting on a wall. The first tile falls because of that wall, not another tile. In the no-boundary case, the wall is geometry itself, a rounded edge, smooth, finite, with no earlier tile. But, in a bounce, the line of dominoes continues, a prior sequence tipping into our own. Either way, the explanation is not myth but mechanism, not fantasy but physics, tested by observation. This is why the cosmic microwave background is so treasured, because it is not philosophy but measurement. It records the state of the universe when it first became transparent. It preserves the acoustic peaks of sound waves from the plasma. Those peaks are red like tree rings, telling us about density, curvature, and matter content. And in those numbers lies the ability to test beginnings, to see whether inflation, bounce, or boundary left their signature. So far, inflation is strongly supported. It predicts flatness, homogeneity, and fluctuations we observe. But inflation itself must have a beginning, and that is why the question of before remains alive. Perhaps eternal inflation extends forever into the past. But theorems suggest incompleteness, that even inflation requires a boundary. Thus we return to the question that began this: what existed before time, if before has meaning at all? Consider a symphony score. The music is real, complete, structured, before a single note is played. In that sense, the no-boundary universe is like the score. The laws and geometry define the conditions, even if no prior time exists. Or imagine a performance where the last fading note becomes mathematically identical to the first rising one. That image is Penrose's vision, cycles without end, beginnings as echoes of endings. The universe does not answer in human tones. It speaks in data, in faint ripples, in photons stretched across eons. We listen with detectors, with mathematics, with patience. And in that listening, we touch the frontier of our knowledge, the edge where questions themselves must be carefully reshaped. Every scientific journey has a frontier, a place where familiar equations weaken and new rules are needed to continue. In cosmology, that frontier is the earliest instant, the place where the Big Bang story itself demands a deeper chapter. The expansion of the universe is measured today with exquisite precision. Galaxies recede, the microwave background cools, the large-scale structure grows as gravity amplifies tiny seeds. But when we ask about the first moment, we run into silence, because the very fabric of time is caught up in the question itself. Think of standing at the shore of an ocean. The waves reach your feet, the horizon stretches ahead, but you cannot see what lies beyond. Physics is like that horizon. The further we push our instruments, the closer we come to a boundary we cannot cross with current tools. Still, we find ways to infer. The tide leaves shells on the beach. The foam carries patterns. The sky above hints at unseen lands. So it is with the cosmos. The faint radiation, the distribution of galaxies, the quiet pull of gravity. These are the shells, the foam, the patterns. The arrow of time is one of those patterns, written in the cooling of stars, the fading of heat, the spreading of disorder. If we follow that arrow backward, we expect entropy to decrease. Yet the early universe was in a state of astonishing low entropy. This paradox is often overlooked, but it is at the heart of the question of beginnings. Why was the cosmos so smooth, so ordered, so unlike the chaos that gravity prefers to sculpt? Roger Penrose called this the whale curvature hypothesis, the claim that the early universe had an unusually vanishing curvature, suppressing gravitational clumping. That condition gave rise to a low entropy start, and in turn allowed the arrow of time to flow forward. But why should such a condition hold? Why should the universe begin with such a special arrangement? Perhaps the answer lies in physics we do not yet know, perhaps in a principle that selects smoothness, or in a multiverse where only smooth patches give rise to observers. Inflation is often suggested as the solution by stretching any initial state into flatness and homogeneity. It works remarkably well at producing the seeds of structure we observe, but it too requires a beginning, a condition that sets inflation going. The inflaton field, the hypothetical engine of inflation, must begin in the right place, and the question of why it did so remains open. So inflation shifts but does not erase the mystery. It gives us a mechanism, but it leaves us with a deeper why. Let's return to the balloon analogy. As the balloon inflates, the dots separate and any irregularities are smoothed. But the act of inflating still requires a hand, a breath, a condition to start the process. In the cosmos, inflation is like that breath. It explains the smoothness, but not the fact that the balloon existed in the first place. And so the search continues for theories that can go deeper, theories that can tell us why there is a balloon at all. One path is the idea of a bounce, where a prior universe contracted and then rebounded into ours. Loop quantum cosmology provides such a scenario. Space and time themselves become quantized, granular at the smallest scales. At high density, quantum geometry resists further compression, just as matter resists being squeezed beyond nuclear density. And in this picture, the universe never reached infinite singularity. Instead, it rebounded, and expansion began anew. The bounce is elegant because it avoids infinities. It replaces the singularity with a smooth transition. It offers a before in the literal sense, a prior era that left its echo in the fabric of our cosmos. Perhaps subtle oscillations in the cosmic background, or statistical imprints in the distribution of galaxies could reveal this echo. But the evidence is not yet clear, and so the bounce remains a hypothesis, waiting for stronger support. Another approach is the no-boundary proposal by Hawking and Hartle, where the beginning is not a point, but a smooth, rounded geometry. In this view, time behaves like space near the origin. It curves, it bends, it ceases to have meaning as earlier or later. Imagine the North Pole of Earth. Ask what lies further north, and the question dissolves. So too does before dissolve in this model. The beginning is not a time, but a boundary condition. Each of these views has beauty, but each must be tied back to data. Cosmology is not philosophy dressed as mathematics. It is a science, and science demands observation. The microwave background is the best testing ground we have. Frozen ripples in light, carrying the fingerprints of the first instance. From those ripples, we test inflation, we constrain bounces, we weigh the geometry of space. Another hope lies in primordial gravitational waves, ripples of space-time itself produced in the earliest moments. They would leave a unique signature, a curl pattern in the polarization of the cosmic background. But such signals are faint. They require detectors of immense sensitivity, instruments cooled and shielded from every interference. The search is underway. Telescopes in deserts, balloons in the stratosphere, satellites above the atmosphere. If we ever detect those waves, the consequences will be profound, a direct glimpse into energies far beyond any earthly experiment. The energy scale of inflation, the shape of its potential, even the reality of a bounce, all could be inferred. Yet the universe has been quiet so far, the signals remain elusive, and the debate continues. Still, silence itself is data. It rules out many theories, narrows the field, guides us toward truth. The idea of a multiverse also enters here, a landscape of regions, each with different laws. In this view, inflation may never end, spawning bubbles eternally, each becoming a cosmos of its own. Perhaps our universe is one bubble among many, one patch where the laws permit stars, galaxies, and observers. But the multiverse raises questions. How can we test what lies beyond our cosmic horizon? Some argue that indirect signals may exist, statistical anomalies, imprints of collisions between bubbles. Others say the multiverse is untestable, and therefore not science, but philosophy. The line between science and speculation must be kept clear. Without data, elegance is not enough. Yet the possibility remains compelling, because it could explain why our universe has the properties it does. Let us return to the arrow of time, for it is central to the idea of before. Entropy grows with time, but if we go backward, we expect disorder to shrink. The early universe was indeed smooth, but why should it have been that way? This question haunts cosmology, for it shapes not only beginnings, but the flow of all time. Imagine once more your cup of tea, cooling as minutes pass, entropy rising. But if we rewind the film, the tea warms, heat flows inward, entropy falls. That is acceptable as fiction, but not as reality, because entropy in reality only goes one way. The cosmos obeys the same rule. Entropy increases, the arrow points forward. So the fact that the universe began in low entropy is astonishing. It is the condition that made everything possible. If it had begun already high in entropy, there would be no arrow, no direction, no complex structures, no memory, no observers. The puzzle of before may therefore be the puzzle of entropy, why the universe started so improbably smooth. And this fact suggests that any theory of beginnings must explain not just expansion, but low entropy. Some turn to anthropic reasoning. We observe this universe because only such conditions allow observers. But such reasoning is not fully satisfying. It explains selection, not cause. The goal of science is deeper, to find mechanisms, principles, laws. And so the search continues across mathematics, experiments, and the patient sky. Perhaps time itself is emergent, a property that arises from deeper correlations. If that is true, then before the Big Bang is a meaningless phrase, like asking what is north of the North Pole. But if the bounce is correct, before has meaning, a prior universe contracting, handing its legacy to us. So the truth depends on which model survives, which matches the data, which passes the tests. We stand at the frontier of knowledge, instruments in hand, questions in mind, humility in heart. The cosmos has revealed much already, but the greatest mystery remains, the nature of time itself. Every candle, every cup, every star we see points to an arrow that began in an ordered state. The search for why continues, and it is in that search that we find both science and wonder. Let's drift quietly toward another corner of the cosmos, where the mathematics of beginnings meets the poetry of existence. Here the questions are not only about physics, but about meaning, about how finite minds can reach toward infinite pasts. We may never see the full answer, but the pursuit itself gives shape to our place in the universe, and the story of before remains open, waiting for the next chapter, the next observation, the next light in the sky. Every beginning we imagine rests on something deeper, a condition, a boundary, a framework that allows it to exist. The Big Bang is often described as the start of everything, yet when we ask carefully, we find that even the bang itself requires explanation. Space and time themselves may not be fundamental. They may be emergent, built from structures or principles beneath our usual perception. The challenge is that our language bends and frays at such depths. Words like before and after lose their everyday anchors. Think of a map that ends at the edge of the paper. Beyond that edge is not more territory, but the limit of the map itself. So, with the universe, when we ask about before the bang, we may be asking about territory that does not exist on the map. But there may also be larger maps waiting to be drawn, frameworks in which our Big Bang is one chapter in a longer story. The task of cosmology is to distinguish between these options and to test them with the few signals the cosmos leaves us. The first signal is the microwave background, the glow of the universe when it first became transparent. From those photons we infer densities, curvatures, and fluctuations. They are fossils of a time long before stars and galaxies. Yet, even these photons are not the ultimate beginning. They come from a universe already hundreds of thousands of years old. To see deeper, we must rely on indirect imprints, statistical patterns, gravitational waves, the echoes of quantum fluctuations stretched across the sky. Inflation provides one such framework, turning microscopic variations into macroscopic seeds. It explains why galaxies exist at all, why stars could form, why planets orbit, why life could one day ask questions. But inflation itself cannot escape the question of origin. What created the inflaton field? What conditions set it in motion? The answers proposed range from quantum tunneling to eternal inflation, but each carries its own puzzles and its own need for deeper context. Bounce models offer a different picture: contraction before expansion, rebirth instead of creation ex nihilo. In loop quantum cosmology, space itself is quantized, discrete packets of geometry that resist infinite compression. As density grows, quantum effects become repulsive, preventing singularity, producing a bounce. And in this view, before regains meaning, a real history, a universe contracting into ours. No boundary proposals take another path, erasing before by curving time into space. In such a geometry, there is no initial instant. Time behaves like latitude near the pole, fading smoothly into nothing beyond. Imagine the globe. Further north than the pole is not defined. In that sense, before the bang is not forbidden. It is meaningless, not part of the geometry at all. Each of these pictures is beautiful in its way, yet beauty alone is not enough. The test is always the sky, the data, the light and matter we can measure. Non-Gaussianity in fluctuations is one such test, a deviation from pure randomness, a fingerprint of particular origins. Another test is primordial gravitational waves, curls of polarization, echoes of space-time's earliest vibrations. So far, the sky is quiet, nearly Gaussian, nearly flat, nearly scale invariant. That silence is instructive. It rules out many wild models. It guides us toward simplicity. Still, we wait for the faintest signals. because even a small detection could reveal the energy scale of inflation or the reality of a bounce. The search is patient. Instruments are refined, missions are planned, the sky is watched. Consider the arrow of entropy again. Every candle, every cup of tea, every cooling star testifies to its flow. The universe began in low entropy, improbably ordered, improbably smooth. Why it did so remains the greatest puzzle, for entropy is the measure of possibility, and the beginning had so few possibilities. Perhaps the answer lies in principles we have not yet discovered, or perhaps in selection across a multiverse of possibilities. The multiverse is controversial. Some see it as inevitable, others as untestable. If true, our universe is one bubble among countless others, each with its own laws, its own conditions, its own arrows of time. But, if untestable, it slips into philosophy, speculation untethered from observation. The boundary between science and speculation must be guarded, or the clarity of cosmology is lost. Still, the multiverse has appeal. It can explain fine-tuned values, the constants that allow galaxies, stars, and life. The cosmos may contain all possibilities, and we find ourselves in one of the few regions where complexity arises. Such reasoning is called anthropic. It explains selection rather than cause. But the goal of physics is deeper, to find laws, mechanisms, causes that go beyond selection. Time itself may not be fundamental. It may be emergent, relational, arising from deeper structures. In this view, asking what came before the bang is like asking what lies north of the pole. The question misuses the word. Yet, in bounce models, before has meaning. A contracting universe, a lineage of causes. And the choice between these views rests on data, not preference, not elegance, but evidence. The future of cosmology lies in new instruments, telescopes mapping the sky with unprecedented precision. Surveys trace billions of galaxies, measuring the growth of structure across cosmic time. Gravitational waves may reveal new windows, signals from mergers, signals perhaps from the earliest epochs, and the hope is that within these patterns lies the key, the signature of what truly happened at the edge of beginnings. Think of the symphony once more, a score written before a note is played. In the no-boundary view, the universe is that score, complete, defined, ready, without need for a before. But in the bounce, the music has been playing longer. Earlier movements echo into our own. Either way, the story is profound, and our place in it is humbling. Perhaps we will never know the full truth, but even the pursuit shapes us. The act of asking these questions ties us to the cosmos, connects our brief lives to the vastness of time. Every detector we build, every survey we conduct, is a gesture of connection, a reaching outward, and the cosmos responds with silence or signal. Either way, we learn. Let's drift now toward quantum gravity, for at the Planck scale, space-time itself must be rewritten. At that scale, lengths and times blur, smoothness dissolves into granularity. Loop quantum gravity suggests discrete quanta of area and volume. Geometry itself is quantized. String theory suggests extended objects vibrating, extra dimensions compactified, a vast landscape of possibilities. Both approaches strive to replace singularity, to give a framework where before may be defined. In string theory, brain collisions could spark expansions, higher dimensional dynamics setting the stage. In loop models, the bounce arises naturally. Discreteness averts infinities. Continuity emerges again. Neither theory is complete. Both are roads still being built. The promise is that someday data will decide. Signals in the microwave sky, patterns in structure, gravitational wave echoes. Until that day, we refine equations, test predictions, build better instruments. Science advances not by sudden leaps, but by patient steps. Each measurement narrowing the field, each theory reshaped by data. And the cosmos rewards patience. It reveals truth slowly but steadily. Think again of the candle and the tea. Small things, ordinary, yet they mirror the universe itself. Entropy grows in your kitchen as surely as in galaxies. Arrows point forward, not back. The universe is comprehensible because the same laws apply everywhere, the same physics in tea and in stars, and that unity is the source of wonder, that from simple laws arises such vastness. So the question of before remains: did time emerge from nothing or from something deeper? Perhaps the answer is beyond reach, or perhaps it is waiting in the next signal we uncover. Either way, the pursuit itself matters because it links us to the origin, to the foundation, to the very fabric of existence. And the story does not end here. It continues as we explore the incompleteness of inflation, the possibility of eternal beginnings, and the strange quiet of the universe at large. Every time we look deeper into the universe, we also look deeper into ourselves. For the questions we ask about beginnings are reflections of our need for roots. The Big Bang gave us a framework of expansion, of cooling, of structure, but it did not tell us why there was a beginning at all. Science is not satisfied with a stopping point. It demands mechanisms, it seeks causes, it asks for laws behind the laws. The search for what existed before the bang is therefore not only curiosity, it is the extension of science to its logical edge. Consider what the night sky shows us. Billions of stars scattered across space, but also stretched across time. Each photon we see has traveled for millions or billions of years, carrying a record of events long gone. In this way, the universe itself is a history book, and we are its readers, deciphering stories from faint light. But the first chapters are missing, hidden behind the veil of opacity before the universe released the cosmic microwave background. The cosmic background is our earliest direct window, light released when electrons combined with nuclei when the fog lifted. Before that moment, the universe was opaque, photons scattered constantly, unable to travel freely. So to go further back, we must rely on inference, on imprints left in later times, on signals carried indirectly. The earliest instants are hidden, but they are not lost. They whisper in statistics, in structure, in the way the cosmos has unfolded. Inflation is one such whisper, a rapid expansion smoothing irregularities, seeding fluctuations. Its fingerprints lie in the scale-invariant spectrum of density perturbations, a near-flat distribution that we measure today. But the exact shape of that spectrum carries information about the energy scale, about the field that drove inflation. And the search for these details is a way of peering closer to the bang itself, because every subtle tilt in the data is a clue to earlier physics. Some models predict detectable gravitational waves, ripples of space-time frozen from the earliest fractions of a second. These waves would create B-mode polarization in the cosmic background, a curl pattern distinct from other effects. So far, we have only upper limits, but even those limits shape theory, ruling out possibilities. The quiet of the sky is meaningful. Silence narrows the map of beginnings as much as signals would. Now, imagine again the arrow of entropy, the candle cooling, the cup losing warmth. The universe began with low entropy, improbably smooth, improbably special. If it had begun in high entropy, no arrow would exist, no complexity, no observers. So the mystery of before is tied to entropy, to why the universe started so ordered. Penrose has argued this puzzle is deeper than inflation, that inflation itself requires a special low-entropy start. In his view, the Weyl curvature hypothesis explains it. The early universe had vanishing gravitational clumping, unlike later times. But this only restates the mystery. Why should the Weyl curvature vanish at the beginning? Perhaps the answer lies in new physics, or perhaps it lies in a principle we have not yet conceived. Bounce cosmologies provide one possible explanation. Contraction erases structure, smoothing the cosmos before rebound. In this picture, entropy is reset in the bounce. The arrow begins again with each expansion. But entropy does not easily decrease, and the details of how it could reset are subtle and contested. The debate continues in theory and simulation, each possibility tested for consistency with what we observe today. No-boundary ideas take a different path, avoiding the question by curving time into space. In this model, before simply does not exist, the question evaporates into geometry. But even then, the specialness of the boundary remains. The condition that produced low entropy still demands explanation. The origin is not erased, it is redefined, moved from a time to a boundary condition. Here is where philosophy and physics meet, at the edge where questions touch meaning. Science cannot ignore meaning, but it reframes it by demanding testable implications, by tying even profound ideas to observation. The universe allows this approach because it is lawful. The same rules apply from teacups to galaxies. So the search for before is not futile. It is part of the same science that explains falling apples and orbiting planets. Let's think about eternal inflation for a moment, a process that never ends, always spawning new universes. In this picture, our Big Bang is one bubble among countless others, each bubble with its own expansion, its own conditions. Collisions between bubbles could, in principle, leave imprints, circles in the microwave background, anomalies in statistics. So far, the evidence is absent, but the search continues because even absence refines the models. Some cosmologists argue that a multiverse explains fine-tuning, why physical constants have values that permit stars and life. If many universes exist with different constants, we should not be surprised to find ourselves in one that allows observers. But this reasoning is controversial. It risks slipping beyond science if it cannot be tested. The line between physics and philosophy must be carefully walked, or clarity dissolves into speculation. The strength of cosmology lies in its discipline. It ties even grand ideas to data. Every model must predict something observable, some imprint in light, some pattern in matter. Without such predictions, elegance is not enough. Theory remains incomplete. And the discipline of science is what makes the story of beginnings more than myth. It makes it a pursuit of truth. Think again of the symphony analogy. The score exists before the music is played. In a no-boundary view, the universe is like that score, complete in itself, without need for a prior moment. But in a bounce, the music is continuous. Earlier movements flow into ours, a lineage of sound. Both pictures are profound, and each invites testable consequences if only we can read the signals carefully. Quantum gravity may hold the key at the Planck scale, where space-time itself is rewritten. In loop, quantum gravity, geometry is discrete, areas and volumes quantized, avoiding singularities. In string theory, extended objects vibrate, extra dimensions curl tightly, a landscape of possibilities emerges. Both approaches aim to describe before, to give structure where relativity fails, to explain what lies at the edge. The difficulty is that testing these theories is hard. Energies are far beyond laboratories, so we turn to the sky as our experiment, to light, to waves, to structure spread across billions of years. Cosmology becomes a particle accelerator of scale, using the universe itself as the collider, and the hope is that within its silence, faint signatures remain, traces of the earliest physics waiting to be seen. Still, we must be humble. Our lifespans are short, our instruments finite. Yet the fact that we can ask these questions is astonishing. That beings on a small planet can probe the first instance of the cosmos. Every telescope, every detector is an extension of us, our senses stretched across time and space, and the universe responds patiently, not with quick answers, but with patterns, data, whispers of truth. So the search for before the bang continues, through inflationary models, through bounces, through no-boundary geometries. Each approach is a step, a possibility, a hypothesis to be tested. The sky is the judge, the photons the witnesses, the galaxies the evidence, and the story is not yet finished, for the silence of the cosmos is as eloquent as its sound. Let's drift now toward entropy once more, for it remains the hidden thread connecting all beginnings. Entropy defines the arrow, the difference between past and future. The low entropy start is the puzzle beneath all others, why it was so smooth, why it was so special. And any theory of before must answer this, or it is incomplete. Every human life is measured by the arrow of time, a clock that moves in one direction, never in reverse. The universe itself shares this arrow. Entropy increases, disorder spreads, and complexity emerges from improbably simple beginnings. But the puzzle is deeper than our kitchens and cities. It is written into the very conditions of the Big Bang itself. The early cosmos was remarkably smooth, far smoother than gravity's natural preference for clumps and collapse. Imagine again a cup of tea left on a table. Heat flows outward, entropy increases, the arrow points forward. In the universe, the same law holds. Stars burn, galaxies evolve, black holes grow. The direction of time is not a mystery in daily life. It is encoded in every cooling object, every decaying structure. But the cosmos asks us a harder question. Why did the arrow begin at all? And why with such low entropy? Penrose highlighted this in the Weyl curvature hypothesis. The idea that the universe began with vanishing gravitational disorder. That condition gave the arrow its first push, allowing entropy to grow from a low base, creating room for complexity. But why this condition held is not yet known. It may be principle or law or simply necessity. The mystery is not erased by inflation, for even inflation requires a low entropy beginning to function. Inflation smooths irregularities by stretching space, turning quantum fluctuations into cosmic seeds. It explains the uniformity we see across the sky and the near-flat geometry measured in the background radiation. but it cannot explain why the inflation field started in the right state, why conditions were suitable for inflation at all. The problem is moved but not solved, shifted from one layer to another, waiting for deeper understanding. Bounce cosmologies approach the problem differently, suggesting contraction before expansion, a reset of the arrow. In such pictures, entropy might be cycled, erased or diluted during contraction before a new arrow begins. But entropy is resistant to reversal, and theories must show exactly how it could reset. The debate is ongoing in equations and simulations, with some promise but no final verdict. No boundary proposals sidestep the arrow by redefining the beginning, curving time into space, erasing the question of before. In that view, the universe has no initial moment, no singular point, only a smooth, rounded geometry. But even then, the low entropy condition remains. It must be explained by the shape of that boundary, so the arrow cannot be ignored. It is central to the meaning of before. Think of entropy as a script. The first act sets the direction, the later acts unfold from it. If the script begins in order, the arrow flows. If it begins in chaos, there is no story to tell. The universe is a story precisely because it began so improbably smooth. And that smoothness is the real mystery. Perhaps the answer lies in principles we have yet to discover, laws that demand order at the start, laws that shape the arrow. Science seeks such laws patiently, through data, through equations, through careful reasoning. We test models against the sky, against photons, galaxies, gravitational waves. The cosmos is the laboratory, the stage, the experiment. And the goal is not only to describe what happened, but to explain why it began this way. Now consider eternal inflation, a process that never ends, always creating new universes. In this view, our arrow is one among countless arrows, each universe with its own entropy story. But eternal inflation raises its own puzzles. It may be incomplete in the past, requiring its own boundary. The incompleteness theorems of cosmology show this. Inflation cannot stretch infinitely backward. So the question remains, why did time start smooth? Why did entropy begin low? Every model must face this challenge. Inflation, bounce, or boundary, none escape it. Perhaps entropy is emergent, a property of deeper physics, not something set by initial conditions alone. Or the truth may be stranger, that before is not time at all, but a state beyond language. Consider, again, the North Pole analogy. The globe curves smoothly, and further north is meaningless. In the no-boundary model, before is like that, erased not by fiat, but by geometry. But geometry itself is a law that must be explained. Why this geometry? Why this curvature? The search does not end in words. It must continue in numbers, predictions, observations. Every theory must meet the same test. It must predict something measurable. Non-Gaussianity is one such test, a deviation in fluctuations, a fingerprint of origins. Gravitational waves are another, ripples of space-time frozen from the earliest times. And the silence of the sky so far is itself data, guiding us, constraining us, shaping theory. So, cosmology proceeds with patience, refining instruments, refining ideas, refining interpretations. The quiet of the universe is not discouragement. It is instruction, telling us where not to look, what not to expect. Still, we hope for the faintest signals, because even a whisper would reshape everything. And the quest for those whispers is as important as the signals themselves. It is the essence of science, the pursuit of truth at the edge of silence. Think of our species again. A few decades of technology, a few centuries of science. The fact that we can ask these questions is extraordinary. That minds born on one planet can probe the origin of time. Every telescope, every detector extends our reach. We see further, earlier, deeper. And the universe allows itself to be read, not easily, not quickly, but slowly, patiently, steadily. So the arrow of time remains the thread, the key to the puzzle of before. Whether through bounce, boundary, or inflation, the low entropy start must be explained. The cosmos invites us to keep asking, to keep building, to keep listening. And the story continues in the silence, where the next signal may finally reveal the truth of what existed before time. Every scientific theory must face the same test. The universe itself must decide whether it survives. Inflation, bounce, or no boundary, each is a possibility, but only observation can tell us which is true. The sky is our experiment, our laboratory, our archive. Photons carry records across billions of years, waiting to be read. And the challenge is to separate signal from noise, to find whispers of beginnings in the silence of space. Think, again, of the cosmic microwave background, a sea of light stretched into microwaves by expansion. It carries the frozen ripples of sound waves in the early plasma, patterns we can measure with extraordinary precision. These patterns are not random. They have peaks, harmonics, fingerprints of physics from the first instance. And from those fingerprints, we learn about density, curvature, and the seeds of galaxies. But cosmologists want more than structure. They want to know what happened before, what set the stage. If inflation occurred, it should have left gravitational waves, ripples in space-time itself, faint but distinct. Those waves would appear as B-mode polarization in the microwave sky, a curling pattern in the orientation of ancient light. The search for B-modes is one of the most ambitious quests in physics because a detection would reveal the energy of the earliest moments. So far, the results are quiet. Only upper limits, only silence. That silence rules out entire classes of models. Theories predicting strong gravitational waves are already gone. Still, the absence of detection does not close the book. It narrows, it sharpens, it instructs. The quest continues in deserts, on mountain peaks, and soon from satellites above the atmosphere. Bounce models too predict signatures, oscillations in the power spectrum, correlations across large scales. Some simulations show faint repeating patterns, as if the cosmos carries memory of an earlier contraction. But so far, the data favor simplicity, no repeating cycles, no strong oscillations. The possibility is not excluded, but the evidence is thin, and the sky has not confirmed it. No boundary proposals make subtler predictions, probabilities for certain inflationary shapes, certain distributions of fluctuations. They favor smoother potentials, plateau-like inflaton fields, rather than steep chaotic forms. And indeed, the data so far favor those plateau models, a quiet alignment between theory and observation. But the match is not proof. It is a hint, an encouragement, not yet decisive. Science advances not with certainty, but with probability. Models rise and fall as evidence accumulates. Each measurement narrows the field, reduces possibilities, strengthens or weakens entire frameworks. The beauty of cosmology is that it deals with the largest questions, yet it answers them with small, precise numbers. and the numbers come from light measured in detectors, from faint ripples stretched across the entire sky. Consider the irony. To learn about the earliest trillionth of a second, we measure microwaves with antennas on Earth. The journey of those photons is unimaginable. Released billions of years ago, scattered across expanding space, cooled into faint radio. Now they are caught by instruments, turned into data, patterns of polarization, maps of temperature, peaks of acoustic sound. And the cosmos reveals itself through those numbers, silent yet eloquent, whispering its truth. Every possibility of before must face this whisper. The bounce, the boundary, the inflationary start. If the bounce is true, there may be statistical echoes, correlations that persist from contraction to expansion. If inflation is true, there may be gravitational waves, the curls in the sky that betray quantum fluctuations stretched across space. The silence of the sky is not failure, it is a guide. Every non-detection trims the field, sharpens the map, brings us closer to truth. Science thrives on silence as much as signal, because silence removes illusion, leaving only what can be real, and the cosmos continues to speak in both ways, in whispers of data and in the discipline of quiet. Now, let us think about the incompleteness theorems, the proofs that inflation cannot extend infinitely into the past. These theorems show that even eternal inflation needs a beginning, a boundary, a starting condition. So, the multiverse, if real, cannot erase the question of origin. It simply moves it one step further back. The why remains. Why is there something instead of nothing? Why did expansion ever begin? Consider also the role of quantum gravity, for at the Planck scale, space-time itself must change. Loop quantum gravity replaces smooth geometry with discrete quanta, tiny packets of area and volume. At high densities, these quanta resist compression, producing a bounce instead of singularity. The idea is elegant, but it awaits data, imprints that could confirm discreteness in the cosmos. String theory offers another approach: vibrating strings, extra dimensions, brains colliding. In some scenarios, our universe was born from the impact of higher dimensional brains, a cosmic collision replacing a singular beginning. But string theory's landscape is vast, a nearly infinite set of possibilities, difficult to test. The hope lies in subtle imprints, signatures hidden in cosmic background or particle physics, but none are confirmed yet. Still, we continue to search, because even absence teaches us, even silence shapes our models. The discipline of cosmology is patience, building theories, discarding them, refining them, always guided by data. Every decade brings sharper maps, deeper surveys, clearer signals, and the cosmos answers slowly, but it does answer, with photons, with structure, with gravitational echoes. Think once more of the candle and tea, small symbols of the arrow of time. The cosmos is vast, but it obeys the same rules. Entropy grows, order gives way, the arrow points forward. But the low entropy beginning remains unexplained. The fact that makes the arrow possible is still the greatest mystery. So the question of before is really the question of order. Why the universe began so improbably smooth. Some argue that anthropic reasoning is enough. We exist in such a universe because only such a universe allows existence. But the goal of science is deeper. Not just to note selection, but to find causes. Every model that survives must explain order. must show why entropy was low at the beginning, and the universe demands this answer, for without it, the arrow of time remains a puzzle unfulfilled. So, we search in silence and in whispers, in data faint but measurable, in patterns across the sky. The truth of before will not be myth or legend. It will be measured, tested, confirmed. Science will not stop with a singularity. It will seek what lies beneath, what rules apply at the edge, and the story of before remains open, waiting for the next whisper, the next clue, the next light in the darkness. Every age of science has faced its horizon, a place where old tools no longer suffice and new ideas must be forged. The cosmos challenges us with its greatest horizon, the beginning of time itself, the point where equations dissolve and intuition stumbles. But this horizon is not a wall, it is a frontier, an invitation to push further, to think more deeply, to measure more carefully. And the frontier of before the Big Bang is the most profound of all, for it asks whether time, space, and order themselves have origins. Consider again the incompleteness theorems, proofs that even eternal inflation cannot stretch infinitely backward. The math shows that any expanding universe must have a boundary, some condition where the arrow begins. So, whether we imagine inflation, bounce, or multiverse, we cannot escape the question of first cause. The why of beginnings lingers, patient, unyielding, waiting for answers in physics we have not yet discovered. Quantum gravity is the likely key, for only by merging quantum mechanics and general relativity can we describe the earliest instant. Loop quantum gravity gives us discreteness, geometry itself reduced to quanta, area and volume broken into fundamental units. At high densities, these quanta push back, avoiding singularity, producing a bounce instead. The picture is graceful, but not yet proven. It requires signals, imprints, whispers from the cosmos to confirm. String theory offers another path, vibrating strings and higher dimensional brains, a vast landscape of possible beginnings. In some visions, our universe was born of a brain collision, a higher dimensional event leaving behind expansion and heat. But the landscape of string theory is immense. Too many possibilities, too few clear predictions. The hope is that subtle signatures in cosmology or particle physics might guide us, narrowing the field, testing the framework. So the frontier is not barren, it is full of possibilities, but short on decisive evidence. The task of cosmology is to test where we can, to prune what does not fit, to keep what survives data. Science is not impatient. It advances slowly, by elimination, by refinement, by persistence, and the cosmos rewards patience. Even silence teaches, even absence of signal shapes understanding. Now, consider entropy again, the arrow that defines past and future. The low entropy start is still the puzzle beneath puzzles, why the beginning was so improbably ordered. Penrose argued that smoothness itself was the miracle, for gravity prefers clumps, black holes, chaos. So the early universe defied gravity's preference, beginning instead in a special state of uniformity. Inflation smooths irregularities, but requires a smooth start. It does not erase the puzzle, it reframes it. The bounce offers resets, but entropy resists resetting. Disorder prefers to grow, not to shrink. No boundary geometries erase before, but they too must explain why the geometry selects low entropy. And the question of entropy remains the core, the arrow, the improbable order, the beginning of beginnings. Think of a domino line resting against a wall. The first tile falls not because of another, but because of the wall itself. In a no-boundary model, the wall is geometry, a boundary condition rather than a prior moment. But in a bounce, the line extends backward. Earlier dominoes fall, contraction becomes expansion. The difference is profound. One erases before, the other restores it. Either way, science must test predictions. Models are not poetry. They must face the sky. Primordial gravitational waves are one test, ripples in space-time frozen from the earliest instant. So far we have silence, upper limits but no detection. The absence of waves removes wild models, sharpening the map of possibility. Non-Gaussianity in the cosmic background is another test, a deviation from perfect randomness. If the fluctuations were not purely Gaussian, it would betray mechanisms of origin. But the data so far show near Gaussianity, simplicity, calmness, no wild deviations. The quiet of the sky again instructs. It narrows, it guides, it refines. Still, cosmologists persist. Because the stakes are ultimate, the origin of time itself. The search extends across galaxies, across polarization maps, across gravitational wave observatories. Every new survey adds clarity, billions of galaxies mapped, structures traced across cosmic time. And the cosmos speaks through these maps, telling us how matter clustered, how expansion unfolded, how beginnings left their mark. Think of the irony. Beings on a small planet measure the first trillionth of a second. The fact that photons, stretched across billions of years, still carry this information is astonishing. Every telescope extends our reach, turning faint whispers into knowledge, into numbers, into understanding, and the knowledge binds us to the cosmos, our origins written in light older than galaxies. So, where does this leave us? Bounce, boundary, inflation, multiverse. Each possibility has beauty, each has puzzles, none yet has proof. Science demands proof, demands testable signals, demands data. And the data so far favor simplicity, flatness, homogeneity, Gaussian fluctuations, silence in waves. Perhaps the truth is stranger, beyond our metaphors, beyond our maps. Time may be emergent, not fundamental, arising only from deeper correlations. In that case, before is meaningless. The question evaporates into new physics, but the search remains essential. For only by pushing against the question do we learn what words and ideas no longer apply. Every generation of science reshapes the frontier. What was once philosophy becomes physics. What was once mystery becomes measurement. The origin of time may follow the same path, from speculation to theory to observation. Perhaps one day we will map the bounce, or prove the boundary, or detect the waves of inflation. Until then, the story is incomplete, a score with missing notes, a symphony still waiting for its opening bars. Let's drift quietly toward another corner of the question: the role of human meaning in cosmic beginnings. The fact that we ask about before the bang is itself remarkable. Tiny beings in one galaxy, reaching for the edge of time. Every culture has imagined origins, has told stories of beginnings. But the difference now is that our story is not only myth, it is testable, it is written in data, it is science. Every question about the cosmos is really two questions. What happened, and how do we know? The Big Bang is not just a theory of expansion, it is an explanation supported by layers of observation. But when we ask about before, we move from well-tested ground into uncharted possibility. And the only way forward is the same as always: to measure, to test, to listen for what the universe will reveal. Consider the silence of gravitational waves so far. No detection of primordial B modes, only upper limits. This quiet has already removed many models. Theories predicting strong signals have been cut away. But silence is as important as discovery. It prunes, it guides, it shapes the field. The absence of evidence narrows possibility, teaching us where truth cannot be. Inflation remains the leading idea, explaining flatness, uniformity, and structure. Its predictions match the data well, nearly Gaussian fluctuations, nearly scale-invariant spectra. But inflation alone is not enough. It cannot explain why the inflaton existed, why entropy was low, why expansion began. The mystery of before remains, even within inflation, unanswered, unresolved, waiting for deeper physics. Bounce cosmologies tempt with elegance, no singularity, only contraction turning to expansion. In loop quantum gravity, discreteness prevents infinities. Space resists compression, rebounds instead. But evidence is thin. No confirmed oscillations, no repeating cycles, no clear memory of contraction. The possibility is alive, but fragile, a framework still waiting for decisive proof. No boundary proposals change the question, erasing before by redefining beginnings. In such a geometry, time curves into space. There is no initial instant, only a smooth boundary. But even here, the puzzle of low entropy survives. Why this boundary? Why this special condition? So the arrow remains central. The direction of time itself is the heart of the mystery. Think of entropy as the grammar of time. It makes sentences possible. It gives direction to the story. Without low entropy at the start, the arrow would never rise. Memory would not exist. Futures would not unfold. The beginning of time is therefore the beginning of grammar, the rules that make history and prediction possible. And the fact that the universe began so improbably smooth is the deepest clue we possess. Science demands mechanisms, not only description, and the search for mechanism is relentless. We map galaxies across billions of light years, tracing how matter clustered under gravity's pull. The pattern of clustering carries echoes of beginnings, tiny seeds stretched by inflation, amplified by expansion. And the patterns align with theory, not perfectly, but closely enough to inspire confidence. Still, cosmologists push further, searching for non-Gaussianity, for subtle correlations, for anomalies. The cosmos is patient, but not random. Its silence is structured, its whispers repeatable. Every new survey adds data, billions of galaxies measured, trillions of photons recorded. And the universe speaks in statistics, faint trends that point back toward its origin. Perhaps the next signal will come from gravitational wave detectors, listening not only to black hole mergers, but to the hum of the cosmos itself. The background of gravitational waves, if detected, could reveal the scale of inflation or rule it out entirely. So far, only silence, but silence narrows. Silence is progress. And the sky is vast enough to hold answers still hidden, waiting for instruments precise enough to hear them. Consider, too, the role of meaning, for human beings cannot help but see themselves in these questions. The fact that entropy began low is not only physics, it is the reason why memory exists, why we can tell stories, why we can build science. If entropy had begun high, no complexity would arise, no galaxies, no stars, no planets, no minds. So the mystery of beginnings is also the mystery of ourselves, why the conditions exist that make thought possible. Some invoke the multiverse, countless universes, each with different laws, only some capable of producing observers. In that view, our ordered beginning is not unique, it is selection, not miracle. But this reasoning remains controversial, because it risks being untestable, beyond the reach of observation. The line between physics and philosophy is sharp here, and cosmologists tread carefully not to blur it. Still, the multiverse remains tempting, for it explains fine-tuned values, constants delicately set. The cosmos, we know, may be one of many, and we simply inhabit a rare bubble where stars and life are possible. But even this requires a mechanism, eternal inflation, quantum branching, or higher dimensional landscapes. And the search for indirect evidence continues, statistical anomalies, patterns that might betray collisions with other bubbles. The discipline of cosmology is not to accept easy answers, but to test even the grandest ideas. Every hypothesis must produce consequences we can measure, or it remains speculation. Even silence counts as evidence, because silence removes possibilities, trims the field, and the cosmos does not flatter us with quick answers. It reveals truth slowly, with patience. Think of science itself as a kind of arrow. Progress flows forward, theories evolve, models refine. The universe teaches us humility, for every answer births new questions, every explanation deepens mystery. And this humility is not weakness, but strength. It keeps us honest, it keeps us searching. The story of before is unfinished, but its pursuit shapes our place in the cosmos. Every candle, every cup, every cooling star reminds us that the arrow began low, improbably smooth. That smoothness is not trivial. It is the foundation of time, the reason futures exist. Inflation, bounce, boundary, multiverse, each tries to explain it. None yet succeed fully. So the puzzle remains, luminous and silent, guiding inquiry forward. Let's drift toward the frontier of quantum information. For some suggest time itself may emerge from entanglement. In that view, correlations, not clocks, create temporal order. Time arises from relationships, not from background flow. Perhaps, then, before the bang is not time at all, but a network of correlations, a state beyond familiar categories. And the arrow could arise from asymmetry in those correlations, entropy growing because relationships unfold in only one direction. The implications are profound, time not as a container, but as a construct emergent from deeper physics. If true, then the question of before dissolves, not meaningless, but misframed, a category error of language. Still, even emergent time must leave imprints, correlations in the cosmic background, anomalies in structure, and the search continues for such evidence, delicate, subtle, but within reach of future instruments. Every theory we craft is provisional, a scaffold, not a temple. The history of science is proof of this. Newton gave way to Einstein, classical gave way to quantum. So too will our current theories give way, refined, expanded, perhaps replaced. The cosmos is larger than our metaphors, deeper than our present frameworks. And so we continue, patient and persistent, listening for whispers, measuring silence, testing beginnings. The arrow of science, like the arrow of time, flows forward, never reversing, always moving toward greater order of knowledge. Before the Big Bang may remain mysterious, but mystery itself is the fuel of progress, and the journey matters as much as the destination, for it binds us to the universe and the universe to us. Every horizon we approach is both a limit and an invitation. We cannot see beyond, but we can imagine what lies there. The Big Bang is such a horizon. It is the edge of our tested knowledge, the place where physics demands new invention. But imagination alone is not enough. Science requires that imagination be disciplined, shaped by evidence, and the task of cosmology is to weave imagination with data, to extend thought without losing contact with observation. Consider the Planck time, the smallest slice of time that physics can currently define. It lasted only 10 to 43 seconds, a scale so short that human language breaks under its weight. At this scale, quantum fluctuations of space-time dominate. Geometry foams, smoothness dissolves, certainty evaporates. The classical universe we know emerges only after this, when general relativity and quantum fields settle into describable form. So, the true question of before is really the question of Planck-scale physics. What laws apply when time itself is granular? Loop quantum gravity imagines discreteness, geometry made of finite quanta. String theory imagines extended vibrations, tiny strings weaving the fabric of space-time. The truth may be neither or both, but it must be something, for the singularity is not the end of explanation. Think again of the North Pole analogy. Beyond the pole, the map does not extend. In a no-boundary model, before is like this, not forbidden, but undefined, a curve instead of a wall. But if the bounce is real, then before regains meaning. Contraction gives way to expansion. History extends further back. The difference between undefined and extended is profound. One ends the question, the other deepens it. Every approach must still face entropy, the arrow that defines direction, the puzzle of smoothness. Inflation spreads irregularities into near uniformity, but needs a smooth start itself. The bounce could recycle entropy, but mechanisms remain unclear, resistant to proof. No boundary geometry evades time, but not the improbability of order. So entropy remains the central whisper of evidence, the clue that any complete theory must explain. The fact that the cosmos began in such an ordered state is extraordinary against all natural tendencies of gravity. Penrose saw this clearly. Smoothness itself was the great miracle, not expansion alone, and the miracle demands law, something deeper than chance, something woven into the foundation of physics. Perhaps quantum information will provide the clue, entanglement creating time, order arising from correlation. In such a view, time itself is emergent, not background, but relationship. But emergence must leave fingerprints, correlations measurable in structure, anomalies in fluctuations, and the search for those fingerprints is underway, subtle, statistical, patient. Think of science as a lantern in the dark. It cannot illuminate everything at once, but it reveals step by step. The lantern of cosmology has revealed galaxies, expansion, microwave light. Now, it seeks the first instance, the Planck era, the before of time, and the light of this lantern comes from instruments, satellites, detectors, maps of cosmic structure. Every map of galaxies is a history of clustering, tracing how small fluctuations grew under gravity. The pattern we see today is the fossil of beginnings, stretched across billions of light years, but rooted in the first moments. So, by mapping galaxies, we read history, not just of stars, but of time itself. The fact that the large-scale structure matches inflation's predictions is remarkable, but it still leaves deeper puzzles. bounce cosmologies would produce different statistical features, correlations across scales, echoes of contraction. So far, the data have not confirmed these, but neither have they ruled them out entirely. No boundary proposals favor specific inflationary shapes, plateau-like potentials, and the observations of the microwave background lean gently toward these shapes, an intriguing but incomplete alignment. Still, no single model has triumphed. Each is partial, each is tested but not proven. The strength of science lies here, not in certainty, but in the ability to refine and discard. Every silence of data is progress, pruning what cannot be true, shaping what remains, and the cosmos cooperates slowly, patient, deliberate, revealing its truth one clue at a time. Consider the possibility of eternal inflation again, a multiverse of bubbles, each with its own arrow of time. In this landscape, our ordered beginning is not unique. It is selection, not necessity. But collisions between bubbles might leave imprints, faint circles in the microwave sky. So far, the search finds no such circles. But even that absence teaches, narrowing the plausible. The multiverse is not an escape. It too requires explanation. It too must be tested. If true, it explains fine-tuning, but shifts the puzzle. Why does the larger landscape exist? What law underlies it? Science cannot rest with infinite regress. It must still ask why there is something rather than nothing. And the question of first cause remains, even in a multiverse of endless beginnings. Think of human history for a moment. Every culture has asked about origins. The difference now is not the question, but the method. We ask with data, with numbers, with predictions. Every myth was a kind of hypothesis, but untested, unrefined, unmeasured. And the journey from myth to cosmology is the story of science itself. So, the horizon of imagination is not the end. It is the beginning of new science. The task is to discipline imagination with evidence, to keep wonder tied to observation. Inflation, bounce, boundary, multiverse, each is an imagined extension. But the cosmos will decide which survives, with silence or with whisper, with data or with anomaly. And, as we stand on this frontier, the questions deepen. Is time fundamental, or emergent, or cyclical? The answers may reshape not only cosmology, but physics itself. Perhaps time is a construct, born of entanglement, dissolving at the Planck scale, or the truth may be cycles without end or boundaries without before. Every attempt to describe before the Big Bang runs into the same obstacle, the nature of nothing itself. The word nothing seems simple in ordinary language, but in physics, nothing is one of the hardest things to define. In daily speech, nothing means absence, an empty cup, a bare room, a blank page. But the cosmos teaches us that emptiness is never truly empty. Quantum fields seethe, energy flickers, particles appear and vanish. So, the vacuum is not a void. It is a stage with actors unseen, always at work beneath perception. The quantum vacuum is filled with fluctuations, brief appearances of particle pairs, virtual but real in their effects. Casimir forces between plates, shifts in atomic spectra, the weight of vacuum energy, all reveal that nothing has substance. And the idea that our universe could emerge from such a vacuum is one of the boldest in cosmology. Perhaps the Big Bang was a quantum fluctuation, a tunneling event from a prior state of nothing-like vacuum. But the question immediately follows: what law governs such fluctuations? what defines the stage on which they occur. Even nothing requires rules. Even a quantum vacuum is structured, defined by fields and laws. So the mystery deepens. Why do the laws themselves exist? Why is there something instead of absolute absence? Think of an empty chessboard before a game begins. It looks bare, but the rules are already there, shaping what is possible. The vacuum of physics is like that board. No pieces, yet the rules of movement exist, ready to be played. So, when we speak of nothing in cosmology, it is not absence of law, but the presence of possibility without matter. And the laws themselves may be the ultimate puzzle, why they exist, why they have the form they do. Every step we take pushes the question back. Inflation explains structure, but asks why inflation began. Bounce models avoid singularity, but ask why cycles exist. No boundary geometries erase before, but ask why such geometry holds. And the multiverse explains fine-tuning, but asks why the multiverse itself exists. So, the weight of nothing grows heavier the more we ask. Absence reveals itself as presence, silence as structure. The frontier is not a place of void, but of hidden depth. Perhaps the very distinction between something and nothing is flawed. Perhaps laws and states are inseparable, always present in some form. And the truth of before may be that before is not absence, but a different kind of presence we cannot yet name. Consider again entropy, the smooth beginning, the improbably ordered start. That order itself may be the mark of law, a sign that the rules of nothing prefer simplicity, not chaos. But we do not know why order would be preferred, why smoothness, not disorder, would be the boundary. The cosmos leaves us with a riddle, one that data alone may eventually solve, but not yet. Every photon we catch is part of the answer. Each carries memory of earlier times. The microwave background remains our best witness, a faint sea of light frozen since the universe became transparent. So, we study its temperature, its polarization, its small fluctuations, and the numbers extracted from it reveal conditions with astonishing precision. Densities, curvatures, compositions. But the numbers also carry limits. They can only tell us what happened after a certain time. Before recombination, the universe was opaque. Photons could not travel far, memory was scrambled. So, to probe further, we rely on indirect signals. Imprints carried into later times, statistical echoes. The hope is that in these echoes lies the story of before, written subtly, waiting to be read. Gravitational waves are one such echo. Ripples in space-time from the earliest instants. Their detection would be revolutionary. Proof of inflation, a glimpse into Planck-scale physics. But silence so far has been instructive. Many models already ruled out, simplicity favored. And the search continues with relentless patience. Detectors scanning sky and ground, waiting for whispers. Think of how remarkable this is. Creatures on one planet listening for ripples in space-time itself. The journey of science is as humbling as it is grand. From apples falling to the birth of universes. Every new observation ties us more deeply to the cosmos, reminds us that we are participants in its story. And the story of before the Big Bang is the most profound chapter yet to be written. So, nothing is not truly nothing. It is vacuum, law, possibility. The debate continues whether universes can tunnel from such states, or whether deeper principles are required. Quantum cosmology treats the universe as a wave function, probabilities replacing certainties, beginnings as distributions, and the idea that our universe could simply be one solution among many is both bold and sobering. Perhaps, then before, is not a single history, but a probability cloud, a spread of possible origins. In such a view, our universe is one realized path, one actualization of many that could have emerged. But probability itself requires rules. The wave function requires equations, the equations require form, and the puzzle returns. Why these rules? Why this form? Why not nothing at all? Every attempt at final explanation seems to circle back. The question never dissolves, it shifts. The multiverse shifts it outward, the bounce shifts it backward, the boundary shifts it into geometry. So far, none erase it, none resolve it entirely, and the mystery remains luminous, a horizon that pulls thought forward. Think of horizons in human life. We never reach them, but they guide our path. The cosmos itself sets horizons, the speed of light, the limits of observation, the beginning of time. Yet, each horizon we approach transforms us by the act of seeking even before answers arrive, and the seeking of before may be less about arrival than about transformation. Every mystery feels endless when first encountered, but over time, patterns appear and structure emerges from the fog. The Big Bang once seemed impenetrable, a singularity, an absolute wall of ignorance. But today the fog has lifted slightly. The outlines of possible answers are visible, even if details remain hidden. And the clarity we have gained is that the beginning is not beyond reach. Physics can and does speak about it. Consider how far we have come since the early 20th century, when the universe itself was thought eternal and static. The discovery of expansion changed everything. Galaxies receding, space stretching, history opening behind us. Then, the cosmic microwave background revealed itself. A sea of ancient light, proof of a hot, dense past. And the evidence grew layer by layer. Structure, nucleosynthesis, precision maps, each confirming expansion. So today, we know with confidence that the universe had a hot beginning, a time when matter and radiation were dense and uniform. The clarity begins here. The Big Bang is not myth, but measured fact. From this fact, new questions arise. What happened before? What set it in motion? What shaped its conditions? And the answers are no longer entirely obscure. They are constrained, narrowed, given form by observation. Inflation is one of those answers made clearer, no longer speculation, but supported by strong evidence. Its predictions match the sky. Flatness, Gaussian fluctuations, nearly scale-invariant spectra. But clarity also comes from knowing its limits. It does not explain low entropy. It cannot extend infinitely backward. So the picture is sharper than before. Inflation is real, or near real, but not the final word. Bounce cosmologies have also clarified their role, no longer vague speculation, but structured models in loop quantum gravity. They replace singularity with a rebound, contraction yielding to expansion, geometry resisting infinite density. And, while evidence is not yet decisive, clarity has grown. We know what such models would predict, what signals to seek. So the bounce is not merely idea, but a scientific hypothesis, a candidate awaiting judgment by data. No boundary proposals too are clearer now, their implications calculable, their predictions defined. They favor certain inflationary shapes, certain potentials, certain distributions of fluctuations. But clarity also means we see their weakness. They rely heavily on interpretation, and evidence is indirect. Yet the fact that such abstract ideas can be tested at all is progress, clarity where once there was only philosophy. Entropy, too, has become clearer. The low entropy beginning is no longer vague surprise, but precise puzzle. We know how smooth the early universe was, measured in fluctuations compared to gravitational collapse. The improbability is calculable, not hand-waved, billions upon billions against chance. And the clarity here is sobering. The arrow of time requires explanation, and any true theory must provide it. So clarity emerges not by final answers, but by narrowing possibilities. Not all ideas survive contact with data. The cosmos has pruned wild models already. Chaotic inflation, strong waves, exotic geometries that fail the numbers. Every silence has been instructive. Every absence of detection has been progress. And the progress is real. The horizon of before is closer today than it was a generation ago. Think of the microwave background again, once just faint static, now a detailed map. Its ripples are the clearest evidence of inflation we have, fingerprints of quantum fluctuations made cosmic. But clarity comes also from knowing what is missing. No strong gravitational waves, no sharp non-Gaussianity. The absence is as telling as the presence. Data paints outlines which are enough to guide theory. Gravitational wave observatories sharpen this further, listening not only to mergers, but to cosmic hum. The silence they have found so far already rules out high-energy models of inflation, a narrowing, a sharpening. So, we are left with plateau-like potentials, quiet models, smoother beginnings, and the fact that theory and data align here gives confidence, clarity where before there was doubt. Bounce predictions have also sharpened. Simulations reveal exactly what signatures would remain. These signatures include oscillations, correlations, repeating patterns. But the data show no clear cycles yet. Silence once again narrowing, shaping. So the bounce is not disproved, but constrained, clearer than before, not free imagination, but tested structure. No boundary predictions too have been tested. Probabilities assigned to certain inflationary landscapes. They favor what data favors. Smoother potentials, flatter beginnings. And, while indirect, the alignment is real. A hint that geometry may indeed erase before. So the clarity is not certainty, but probability. A fog thinned, not vanished, but navigable. Perhaps the greatest clarity is in the recognition of limits. We know what questions are meaningful, what are not. To ask what is north of the pole is not meaningful, and to ask what is before time may be the same. The clarity lies in knowing this difference, in seeing where language fails, where physics reframes, and the truth may be that some questions dissolve rather than resolve, clarity by transformation, not by answer. Still, science does not surrender easily. It seeks every possible whisper, every measurable clue. We map galaxies, detect waves, measure light, simulate origins. The frontier is alive with data, not barren with ignorance, and the clarity grows as models fall, as survivors sharpen, as evidence accumulates. Think of a candle's flame through smoke, at first blurred, then slowly sharpening into shape. The cosmos is like that flame, faint but real, increasingly clear through the haze of ignorance. Every measurement is a gust of wind clearing smoke. Every silence is another contour revealed, and the flame, now is the outline of beginnings, not final, but visible enough to pursue. So what do we know clearly today? We know the Big Bang was hot and dense, not myth, but measured. We know inflation, or something like its smoothed and seeded structure. We know entropy began low, improbably, demanding explanation. We know bounce, boundary, and multiverse remain possible, but not equally likely. And the clarity is that the mystery has shrunk, not solved, but framed, bounded, defined by data. Every puzzle of before is made of threads: entropy, inflation, geometry, quantum gravity, all woven into one fabric. The clarity we have reached is not a final picture, but a tapestry of possibilities, each constrained by data, each shaped by silence. But even in incompleteness, coherence has emerged. We see how the puzzles connect, how each thread tightens the others. And the story of before is no longer formless. It has structure, boundaries, meaning. Consider entropy again, the first thread, the arrow of time born of low disorder. This fact is not speculation, but measurement. The smoothness of the early universe is precisely known. So, any theory of before must explain this smoothness, or it is incomplete. The clarity here is sharp. Entropy is not optional, it is central. Inflation is the second thread, an elegant mechanism to stretch space and seed structure. It matches the data astonishingly well. Flatness, Gaussianity, scale invariance, all consistent with observation. But inflation needs its own beginning, a field, a state, a reason to start. So, the thread of inflation ties itself to entropy. Smoothness and inflation cannot be separated. Bounce cosmologies form another thread, replacing singularity with contraction and rebound. They predict echoes and cycles, subtle correlations in the microwave sky. So far, the data show no decisive trace, but the possibility remains alive, constrained but not erased. And the thread of bounce ties to entropy too, for cycles must reset order, must renew smoothness, or they fail. No boundary geometries provide yet another thread, erasing before by curving time into space. They favor certain inflationary potentials, the same ones data seem to favor. But their weakness is philosophical, interpretation, not yet decisive evidence. Still, the thread connects: geometry, probability, smoothness woven into one. The multiverse is a thread more controversial: eternal inflation, bubbles upon bubbles, infinite beginnings. If true, it explains fine-tuning. Our ordered start is one of many, and we simply observe what is possible. But its testability is fragile. Without signals, it drifts toward philosophy. And the clarity here is caution. The multiverse is possible, but not yet proven. Quantum gravity ties many threads together, for only it can truly describe Planck-scale beginnings. Loop quantum gravity offers discreteness, avoiding singularities, producing bounces. String theory offers vibrations and brains, a vast landscape of possible starts. Neither thread is complete, but both are necessary. Both seek to replace singularity with law. So, the threads converge: entropy, inflation, bounce, boundary, quantum gravity. Each alone is insufficient, but together they form a framework of clarity. Every theory that survives must pass 3 tests. It must explain smoothness, match data, and avoid singularity. And the clarity is that only a few threads remain strong enough to pass. Think again of silence in gravitational waves. No strong B modes, no high-energy chaos. This silence already rules out much. Inflation must be quiet, plateau-like, smooth. So, The range of viable models is smaller than ever, narrowed by silence, sharpened by absence, and the absence itself is clarity. The cosmos speaks even when it whispers nothing. The cosmic microwave background remains our greatest map. Ripples frozen from the first 380,000 years. It shows inflation's fingerprints, but no bounce cycles, no bubble collisions. But the alignment with plateau inflation is striking, a hint, not proof, but more than coincidence. And the thread here is strong. Inflation, though incomplete, is more real than myth. Still, entropy looms as the deepest requirement. No theory escapes its demand. The arrow of time points forward only because it began improbably smooth. So inflation alone cannot explain it, bounce must justify it, boundary must encode it. The clarity is this: entropy is the foundation of before, the puzzle that all must solve. Perhaps quantum information holds the key, entanglement giving rise to time, order from correlation. In that picture, before is not time at all, but a network of relationships, a state beyond language. But such states must leave traces, measurable in structure, testable in statistics, and the search for those traces is already underway, clarity advancing slowly but advancing. Think of cosmology as detective work. The scene of the crime is erased, but clues remain. The clues are photons, galaxies, waves, entropy. Piece by piece, the story is reconstructed, not fully, but enough to glimpse the outline. And the outline today is clearer than ever, not final, but not formless. So, what do we see clearly now? We see that the Big Bang was not the beginning of everything, but the beginning of our expansion. We see that inflation almost certainly occurred, though quietly, not violently. We see that entropy began improbably low, demanding deeper law. We see that bounce, boundary, and multiverse remain contenders, but not equally supported. And the clarity is that physics has transformed speculation into structure, mystery into measurable possibility. Every new observation will tighten these threads. Gravitational wave silence, galaxy maps, cosmic background patterns. The future will decide which survive, which fray, which dissolve. But even now, we are not in darkness. The fog has thinned, the puzzle has form, and the threads of entropy, inflation, and geometry hold together, waiting for the final weave in the last part of our story.